Hello and welcome to this session on information retrieval. Today we'll discuss the topic of evaluation. There are several standard test collections that are used in ad hoc retrieval and its evaluation. But before we get into that, let's recap our understanding of ad hoc document retrieval. In ad hoc document retrieval, the system is given a short query queue and the task is to produce the best ranking of documents in a corpus according to some standard metric such as average precision. So this is from Yang, Zhang and Lin of University of Waterloo. So basically what we are trying to say here is that in those earlier good old days, we had drop downs for query field. Nowadays, queries free text field, so the possibilities of the kind of things that can appear in the query is just infinite, so it's huge. um, and we are not constrained to any topic or any such pre-known computable information, so we call this ad hoc document retrieval. So the test collections play a big role in ad hoc document retrieval. That's because we need to use some standard metrics such as average precision. Several standard test collections have evolved. So it all started from the Cranfield experiments in 1950. So now we have the Cranfield collection, which contains about 1,400 documents and 225 queries, and there is exhaustive judgments for all query document pairs. We also have the TREC collection. TREC is Text Retrieval Conference. So we have several data sets here. The one that I have highlighted here is that of 1.89 billion documents with relevance judgments for 450 different information needs. So here we have judgments for top K documents. There is also the Go-To collection. The University of Glasgow maintains a very nice website with links to all these collections. Although if you have to download the Go-To collection, I believe you have to pay some registration and maintenance cost. Of course, you can check it out on their website. So this has about 25 million .gov web pages. We also have the NTCAR, the cross-language information retrieval collection. So here the queries are in one language and we have collection in multiple languages. So that makes a very interesting retrieval task. And then there are several other such standard text collections, such as the Reuters RCV1 collection, which we have referred to in this course multiple times. There is 20 news groups collection, there is ELP collection, Bloomberg. There are many collections out there. Those who are interested in the Cranfield experiments might want to visit the SIGIR Museum. SIGIR is a special interest group on information retrieval. They host a conference every year, the SIGIR conference, uh, which is mostly rated as the top conference for information retrieval. I strongly urge you to go and read about the SIGIR conference and also look up the papers published recently at SIGIR. You should visit the SIGIR Museum if you are interested in knowing about these experiments, especially the Cranfield collection. Okay, with that introduction, let's get into evaluation. The central question here is how to compare search engines and how good is an IR system. So let's say I have built one IR system. The question I have is how good it is and where I should improve it. There are various evaluation methods. We have already seen the precision and recall metric. In this lecture, we would discuss mean average precision, mean reciprocal rank, and NDCG. Let's recap precision and recall. Precision is a fraction of relevant documents and retrieved documents over all retrieved documents, and recall is a fraction of the intersection of relevant documents and retrieved documents over all relevant documents. So these are very useful metrics. We cannot just use precision or just use recall. uh, in which case it's very easy to fool ourselves. So let's say if I want to just optimize my search engine for recall, all I have to do is retrieve everything. Then I would have 100% recall. If I want to not to lose on precision, then the only thing I should do is don't retrieve anything at all. Then I would be good on precision. So let's try out a problem. An IR system retrieves, let's say, 20 documents. They are given below. There are 100 relevant documents in our collection. The hollow squares represent irrelevant documents that were retrieved, and the solid squares uh, uh, represent the relevant documents. Now, what is the precision of my system, and what is the recall? Please pause the video here and work it out for yourself. Yes, the precision is 8 out of 20 because I have 20 documents retrieved and 8 of them are relevant. So the precision is 8 out of 20. And if there are 100 relevant documents in my collection and I have only retrieved 8, then the recall is 8 out of 100. The question now is, can we do better? Can we have just one number instead of two, the precision and recall, to express quality? Indeed, there seems to be one such number, and that is the F metric or the F measure. One measure of performance that takes into account both recall and precision. So F measure is simply a harmonic mean of recall and precision. F is formulated as 2pr over p plus r, or simply 2 over 1 by r plus 1 by p. But why do we need a harmonic mean here? Why not just do an arithmetic mean or geometric mean? Let's take a look. A quick review of the central tendencies. The arithmetic mean of 1, 2, 3 is obviously 2, 1, 2, 3, 4, 5 is 3, 1, 2, 3, 4, 5, 6, 7 is 4. What is the arithmetic mean of 1 to 99? It would be 50. We know this. So if you notice, we are simply taking the central number if it is equally distributed on both sides. But what happens when the series is tail heavy or head heavy? As in this case, we have a tail heavy series with 9 and 10 and just 1. So 1, 9 and 10. So obviously the central tendencies tend towards the right side. So we shift from 5 to 6.7. Similarly here, when I have 1, 8 and 10, I have 6.3 as the arithmetic mean, and when I have 7 and 10, 1, 7 and 10, 6 becomes the arithmetic mean. Alright, so keep this in mind. Let's move on to geometric mean. So geometric mean is simply the nth root of the product of all the terms that I have. So the geometric mean of 2 and 8 would be under root of 2 times 8, which is 4. So now let's try to apply geometric mean to the same series. So I have 7, 8, 9. The arithmetic mean was 8, and the geometric mean would be 7.96. In this case, you can work it out. So 11, 13, 15 would give us a geometric mean of 12.89. So you can notice that geometric mean is little more conservative than the arithmetic mean. Now let's see what happens when we have numbers distributed on one side. So in this case, I have 1, 9 and 10, and the geometric mean tends to be far more conservative than the arithmetic mean, which is 4.48 for geometric mean and 6.7 for arithmetic mean. So you can notice that I have the arithmetic mean becoming more and more conservative as as I tend towards a skewed distribution. Usually we use geometric mean in these kind of contexts where we require some kind of normalization. So the problem here is, let's say if I have computer A, computer B, and computer C, and I'm intending to buy one of them, but I just don't know which one to buy. And let's assume that I have to make that purchase decision solely based on running these two programs and knowing about their time taken to complete. So let's say program 1 on computer A takes 1 second to complete, on B takes 10 seconds to complete, and on C takes 20 seconds to complete. Similarly, I run program 2. Seems like program 2 is a larger program. It takes 1000 seconds on computer A, 100 on B, and 20 on C. Now, given this information, which computer would you like to buy and why? So now that we have two different programs taking two different kind of times, it would be easier to compare the computers if we could normalize these. But how would you approach normalizing in this case, and which kind of central tendency would you use to decide on which computer to buy? If I take the running times on computer A and try to normalize them. So that is, I simply divide program 2's output, 2's time taken by 1000. So I have 1 for here, and then 100 by 1000 becomes zero point 0.1, and 20 by 1000 becomes zero point 0.02. So now I have some standard thing to compare with. So A is the same now, and B and C are changing. So now if I compute the arithmetic mean of both and the geometric mean of both, these are the numbers that you would get. I could also normalize based on computer B. So let's make the computer B's values to be 1, meaning let's divide the first row by 10 and the second row by 100. And then I get 1 for computer B. And now accordingly, the other numbers change. And then I can go ahead and compute the arithmetic mean and geometric mean again. I could also repeat the same thing for computer C. Luckily, computer C has the same numbers for program 1 and program 2. Yeah, let's normalize it to 1. So let's just divide everything by 20, and I get something like this. And if I compute the arithmetic mean and geometric mean, I get these numbers. The question now is, can I decide on which computer to purchase based on the arithmetic mean? The answer is no, because the arithmetic mean is inconsistent across, in giving it gives an inconsistent ranking across normalized values. So if you go with this, it seems like A is the best. It takes the least time than B and C. If you go with this, then it seems like B is the one which gives the least time, and if you go with this, C is the one which gives the least time. So this is inconsistent ranking and is not useful to us. But notice what's happening with the geometric mean. So geometric mean does give very consistent ranking irrespective of which one you choose. It seems like C has the least value when it comes to time taken. So I would probably buy computer C in this case if I have to take a decision solely based on these numbers. So the lesson learned here is that the geometric mean gives a consistent ranking for normalized values. Let's discuss harmonic mean as well. We all know harmonic mean as n over 1 by the reciprocal of x1 plus reciprocal of x2 up to xn, assuming we want to find the mean of x1 to xn. What is the harmonic mean of 2 and 8 then? Let's compute it. It would be 2 over 1 over 2 plus 1 over 8, which gives me 3.2. Let's run it over the same set of numbers that we had before. And if you look at this, it seems like harmonic mean is even more conservative than the geometric mean, which by itself is more conservative than the arithmetic mean. So what is the arithmetic harmonic mean of 1, 9, and 10? So we have 2.48 as the harmonic mean. And you see that it's way too more conservative than the geometric mean and the corresponding arithmetic mean. Usually we apply harmonic mean on whenever there are ratios involved. So for instance, let's assume there's a train moving at 60 kilometers per hour and covers of course 60 kilometers in 1 hour. And let's say the same train returns back with at 20 kilometers per hour speed, it would take 3 hours to complete the journey. So what is the average time taken or average speed? So in these kind of questions, we usually go for harmonic means. But for precision and recall, why do we consider harmonic mean? Please pause the video here and think for a minute. Firstly, we want both precision and recall to go up for the F measure to go up. And that is one reason why we prefer the most conservative measure, which is the harmonic mean instead of geometric mean and arithmetic mean. Secondly, we are also dealing with ratios. Both precision and recall are ratios. So harmonic mean makes a lot more sense than the others. Okay, so the F score, or sometimes called as the F1 score, is a simple harmonic mean of precision and recall. Um, just like we have F1, this one could be replaced with any beta, and we can generalize this formula even more to get a F score, a generalized F measure, which is F beta as 1 plus beta square times the precision into recall over beta square precision plus recall. Notice that if beta is made as 1 in this formulation, you get simply precision times recall over precision plus recall. Um, so if you just make beta as 1, you get the same uh, 2pr over p plus r. So let's go back to our example where we said that we retrieved 20 documents and 8 of them were relevant. Now let me show you a scenario where I built two retrieval systems. The first retrieval system produced this output, the case 1 output, and my second retrieval system produced the case 2 output. Which retrieval system would you prefer and why? All the other factors remain the same. There were only 20 documents retrieved in both, and there were 100 relevant documents in the corpus. So these facts remain the same, just that the order of the first 8 relevant documents have changed. Uh, so which retrieval system do you think is better and why? Of course, the case 2 system looks better because they get the relevant documents at a higher spot, and our intuition is that if there is a relevant document, we would like to see it at the first position. So we don't like this non-relevant document at the first position, for instance. Okay, but our precision recall and F measures treat these two systems as identical or equally good, which is a problem. So we don't like that. So the question is, can we do better for ranked documents? So here is an idea for precision at K. We cut off results at K and compute precision. So let's take an example. The precision at 1 would just take the first result and compute the precision. Since the first result has a non-relevant document, the precision is 0. Precision at 2 would take 2 documents and compute the precision. So we have one of them as relevant, so the precision is half. Precision at 3 would be 2 by 3, and precision at 4 would be 2 out of 4. Now, we could have precision at K to figure out, so we can find out precision at different levels and give more priority to precision at 1 and then to precision at 2 and so on in that order. But even this has a disadvantage that after I've exhausted all relevant documents, adding more and more documents would only reduce my uh, precision value. Similarly, I could also compute recall at k. So I have recall at 1 as 0, recall at 2 as 1 over 100. Note that the denominator refers to the total number of relevant documents that I have in my collection. So this is one way, one metric that people have used. We could also use interpolated precision. Um, so let's take the same example. Here we cut off results at the kth relevance level instead of the kth document. What do we mean? So for precision at 1, we look for the position at which the first relevant document appears. The first relevant document appears at the second position. So we cut off at that relevance level. So meaning we cut off at the second position, and now we compute the precision. The precision is half. If we are interested in precision at 2, then we look for two relevant documents. The second relevant document appears here. So the precision would be 2 out of 3 till here. So if I were to do precision at 3, then I would look for the third relevant document, which is here, and that's 1, 2, 3, 4, 5. So I need at least 5 documents to get 3 relevant documents. So the precision at 3 would be 3 out of 5, and so on till I have n relevant documents. And I could also go for an average precision. The interpolated average in this case is simply 0.5 plus 2 by 3 over 2. So that gives me a value of 0.58. So if we are only interested in two levels of relevance, then this would be my average interpolated precision. What happens for precision at 0? If we are, if so this is a corner edge case. Usually, if you are not retrieving anything, that's the best way. You could never go wrong. So for theoretical analysis, we assume that the precision at 0 is 1. This is just for the sake of completion of this argument. Okay, just like we took an average of interpolated precision, we could also do a simple average precision for precision at different levels. So average of precision at each relevance level could be taken, and in this case, um, the interpolated average precision for this case 1 would simply be half plus half plus half plus half plus half. Uh, that would be half again. Uh, so can you compute the average precision for case 2? Yeah, case 2 works out to be 1 over 3. Um, if there were 10 relevant documents and we retrieved only 5, then the average precision at relevance level of 10 uh, would be 10 on the denominator, of course, and I expect 10 values on the numerator, but I retrieved only 5. So I have values till 5 places, so that's half plus half plus half plus half plus half, and the remaining values are 0, and that's how I would compute the average precision. So can you work out the average precision at relevance level of 4 for this example? Yes, that would be 3 times 1 over 3 plus 0 by 4. A mean average precision makes a lot of sense because we don't want to trust the average precision values for which was taken over one query on our retrieval system. Maybe for another query we perform better, and for another query even better, and for another query really terrible. So what do we do? So it's always a good idea to take a bunch of queries, compute the average precision for each of these queries, and average those numbers up. So that's what we call as the average of average precision, but that sounds bad. So we make this mean average precision, MAP. So the map computes average precision for all relevance levels for a set of queries. So this is simply an average over queries for average precision. So let's assume I have a query one which results in this result set, and only 5 relevant documents are in my corpus. So what would happen to my map? And also compute map for query 2 and query 3, where there are only 3 relevant documents in corpus. Okay, so let's say I have 3 queries, and this is what how the results look like, and these are the number of relevant documents that I have for these queries in my corpus. So given this information, can you compute the mean average precision? Please pause the video here and work it out. Yes, the mean average precision works out to be half plus 1 over 3 plus 1 over 3 by 3. Now consider this question. Can you compute map if you do not know the total number of relevant results for any given query? So if this information is missing, would you be able to compute map? The answer is no. And this is the problem with web search. Judges actually do not know how many relevant documents exist because the corpus is just too huge. Okay, so how to compare two systems if results are not only ranked but graded as well? So let's say the relevance could be highly relevant, less relevant, somewhat relevant, and so on. So if you have a scale of relevance, or as we say, so this is called graded relevance. So if you have graded relevance, then how do I compare two systems? And also, let's make an assumption here that we do not know the total number of relevant documents. Um, so I introduce here the concept of discounted cumulative gain. So discounted cumulative gain, DCG at K, at position K, is given as this formula shown here, where rel R refers to the graded relevance of the result at rank R, and R is the R is of course the rank. Well, okay, so let's look at DCG with an example. So let's assume we have 3 levels of relevance, 0 being the document returned is not relevant at all, 3 being that the document is highly relevant, and 1 and 2 are somewhere in between that range. So the relevance score can go from 0 to 3. So let's assume that we are uh, given a search system which returns documents, 6 documents, and the first document that my search system returned is at relevance level 3. And what is relevance level 3? It's highly relevant, so that I'm happy about this that I got a highly relevant document out. And at rank 2, I have a slightly less relevant document whose relevance grade is 2. And at third position, I have again a relevant document which is 3. Relevance whose relevance level is 3, which means it's a very good relevant document. At relevance 4, I have absolutely irrelevant document, and at rank 5, I have a document whose relevance level is 1, and so on. So I have 6 such documents. Okay, so let's compute rel I over log of I plus 1, and then these are the scores I get. So what I simply do is take a sum of these, and when I take a sum of these, I get a score of 6.861, and that is my discounted cumulative gain. So what's happening over here? If you look at this, my score is directly proportional to the relevance level. So the higher the relevance I get, of course, my value should increase. So that's happening. And I should also punish uh, the documents which have lesser relevance levels, relevance grades. So for example, if I have highly relevant document, which is a document at level 3, at grade 3, then I don't punish the document at all. So I take 3 as it is. But if I get 2, then a not so relevant document, then I punish it. So instead of adding 2 to my gain, I only add a discounted gain, which is 1.262, right? And the discount increases more and more, and that means I punish the bad documents and I don't punish the good ones, right? So if I have an absolutely irrelevant document that is at level 0, then I don't add anything at all. Okay, that's what the denominator is doing for me. And now that I have the discounted values of my relevance, then I take a cumulative sum of all these, and that gives me discounted cumulative gain. So DCG at 6 would mean that I go till 6, the sixth document to compute this number. I could compute DCG at 5 or 4 or whatever I may wish to. So this is considered to be by far a better number than just an F measure, or for that matter precision, or just publishing precision and recall. Okay, so let's say I give you a system where the query returns documents. In the first system returns highly relevant results at the top 3 positions, and for the next 3 position it returns somewhat relevant documents. And there is another system which returns documents graded as these 323, 0, 1, 2. Now, which document would you prefer and why? In this case, intuitively, it's quite obvious that we would prefer the first system because it seems to have more relevant documents at a higher location. And every place, in fact, has a better document than the system 2. So comparatively, we should be preferring system 1. So let's work out the DCG scores and convince ourselves that our DCG system works. So if I have relevance grades here 333, 222, then the amount by which I want to punish is log of I plus 1, which are these. And if I take the ratio, then I get the cumulative gains. I get the gains, and if I add them up, I get the cumulative gain. So this is the discounted cumulative gain, which is 8.74. If I do the same for system 2, I get only 6.86. So I favor 8.74. But you could do this. You could say that you prefer system 1 over system 2 without even doing all these computation, because if you just compare position to position, the each corresponding position has a better document in the first case. So this is easy for us humans to understand. But what if I confuse you with numbers which are not which are difficult for human eyes to perceive? Then this kind of tabulation helps you to arrive at a result. Okay, here is another example where the first system does give you 323012, and the second system gives 333 22210. Now what would you do? Which system do you prefer and why? So what if there are unequal number of documents? So one way to look at this is to look at ideal DCG at 6, which is the best possible value that I can get if I were to cut off at 6 and then normalize both these values. So ideal DCG at 6 is the best DCG across all the systems that I have. If I were to cut down at the 6th position, so obviously it would be the DCG of this second system. And then I could use that number to normalize to get the normalized DCG value, or NDCG as we call it. So NDCG for system 1 would be the DCG of the system 1 over the IDCG value, which is 0.785, and the NDCG for system 2 would be simply 1 because that's the best system I have. Evaluation has been a rich area for research. Every year, SIGIR usually has a track which is dedicated for evaluation metrics and so on. So for those who are more inclined towards this topic, I urge them to go and look up the recent SIGIR papers. SIGIR 2007 had even multiple tracks for evaluation. With that, that's all I have for today. Thank you.